Hello once again, I'm Dr. Linick. In this presentation, we'll take a look at continue to study quadratic functions and in fact look at the standard form of quadratic function and also look at some applications where we can use quadratic functions. So let's look at a little closely what our objectives are. First of all, we want to define the standard form of a quadratic function. Next, we want to examine the properties of the standard form of a quadratic function. We're then going to graph a quadratic function in the standard form. We saw in part 2 of this series on quadratic functions that we graph the quadratic function in the general form. But here we're going to show you how to do the standard form. And some people like graphing the standard form actually a lot quicker than, or a lot better than the general form. Also, we're going to look at the applications of quadratic functions, and we'll take a look at 2 applications involving quadratic functions. All right, so let's go ahead and start in with our definition of the standard form of a quadratic function. The standard form of a quadratic function is f of x is equal to a, then notice we have in parentheses x minus h, in close parentheses quantity squared, plus k. Now what's all involved with that? Well, we have an example here, and that example is f of x is equal to 2 times in parentheses x minus 1, close parentheses squared, plus 5. Well, just as we saw back with the general form, the a here is going to be our lead coefficient. And that's going to also determine whether the parabola opens upward or downward. Next, we have an h and a k, and we'll see that h and k will also be associated with the vertex. And so in the example we have here of the form, we have a whole lot of information about this quadratic function before we even try to graph it or do anything else with it. All right, let's move along to the properties. I know I've got an example here, but I just wanted to show you the example of the form, and then we'll talk about a little bit more what happens with this type of problem. All right, so let's take a look at the properties of the standard form of a quadratic function. Again, that form is f of x is equal to a, in parentheses x minus h, close parentheses squared, plus k. All right, so the vertex is hk. Now notice here that the signs, how the signs fall out. In your function, you have a minus h, but that's going to translate into a positive h with the vertex. Notice k is positive, so it's just going to convert right into k as the y-coordinate of your vertex. So h will be your x-coordinate of your vertex, k will be your y-coordinate of the vertex. Next, we have a similar feature to what we saw previously with regard to the general form of quadratic function. If a is greater than 0, then the parabola opens upward. If a is less than 0, then the parabola will open downward. So again, that's very standard for all quadratic functions, as the lead coefficient will determine whether the parabola opens upward or downward. All right, so let's look at an example, and let's go back to that first problem that I gave you here of f of x, given that f of x is equal to 2 times in parentheses x minus 1 squared plus 5. Okay, so we want to know the end behavior, and the end behavior is what it opens up or down. So we're going to look at a here. So we're going to notice that a is going to be equal to 2. So we notice that our a here is greater than 0. So that means that our parabola opens upward. Okay? It also means, remember, that tells us something about our vertex. It also tells us, before we even find our vertex, since the parabola opens upward, that our vertex is going to be a minimum. Okay? All right, so our vertex will be a minimum. Let me make that look like an M there. All right, and so we're going to have a situation where our parabola looks something like this, where the parabola, again, opens upward, and we've got our vertex down there as a minimum. All right, so next we want to find our vertex. So again, we're going to look and see that our vertex is going to be h comma k, and we know that this is in the form of a times x minus h squared plus k. All right, and so what's going to happen here is we're going to look and see that our h is going to be 1. I know there's a negative there, but remember you're going to ignore that negative here for the time being and just do the opposite. And so h is going to be positive 1, and then k is going to be equal to positive 5. So our vertex is going to be 1, 5 from the equation. So notice we learned a lot about this quadratic function without even having to put the actual graph together yet. And we'll do that a little bit later on. Okay, let's look at a second example. Example 2 is f of x is equal to negative 5 times, in parentheses, x plus 3, close parentheses, squared, minus 4. All right, so once again, we want to know the end behavior. So we're going to see that our a is going to be equal to negative 5. So there's negative 5, that's our a. So what happens? A is going to be less than 0. So this parabola is going to open downward. All right, so this opens downward. And so we have a parabola that's doing something like this. It's opening downward. And so next what we're going to happen, and again, I just draw a picture of the parabola with the two ends pointing downward and having a maximum there for the vertex. So here your vertex is going to be a max. I'm just going to abbreviate that to max here. So, and that's where your vertex is going to be. All right, so, and we've determined the end behavior, and while we're at it, we might as well determine, whether the vertex is a maximum minimum. Now we're going to determine the vertex. All right, and something happens a little bit differently here that we want to consider as we look at this. And we want to remember that we're working off the general standard form of f of x is equal to a times x minus h squared plus k. All right, so what we have to do with this is we want to look at this a little bit differently, because notice that our sign here in between the x and the 3 is positive, and our sign in front of the 4, which is our k, is negative. So this is opposite to what we think. And so basically what's happening here is we really need to rewrite this model of f of x is equal to minus 5 times, in parentheses, x minus a minus 3 quantity squared plus a negative 4. Now the advantage of rewriting this is we can find our vertex from that fairly quickly. And I need one more parentheses in here after this 3. Okay? And so what's going to happen then is we're going to see that the signs change on h and k from what we saw in the previous example. So what happens is, since we have a positive, anytime you have a positive before your h, what's going to happen there is then h is going to be equal to negative 3, and k is going to be equal to negative 4. Since again, it's not plus 4, it's, it should be plus k, but there's a minus there, so that's a plus a minus 4, so k is negative 4. So our vertex here is going to be minus 3, comma, minus 4. All right, and so we found the end behavior and the vertex of this quadratic function in standard form. Okay, next let's look at graphing quadratic functions in the standard form. And so we're going to start out with this example of f of x is equal to 3 times x minus 1 in parentheses, the x minus 1 squared in parentheses, plus 5. Now, similar to what we saw with graphing quadratic functions in the general form, we're going to first of all determine the end behavior. Next, we're going to find the vertex. We're going to determine or find the axis of symmetry. We're also going to find the x-intercepts if they exist, as I noted in a previous program that sometimes they don't exist as far as you get a square root of a negative underneath your radical in the quadratic formula, so you get complex intercepts that are not real numbers. Then we're going to find the y-intercept, and then we're going to use the y-intercept to find another point, similar to what we did in the previous program, but we'll go through that whole thing here if you possibly have forgotten how we did that. All right, so let's start into it. So we're going to determine the end behavior. So notice that a is going to be equal to 3, so a is greater than 0, so we know that the parabola opens upward. All right, so generally we're going to see that we have a situation where the parabola opens upward. And so kind of like a, a U here is what I've kind of drawn on the screen as far, but with arrows to kind of mimic the general shape of the graph. All right, next we're going to find the vertex. Again, we're going to come up here and we're going to look at the vertex, and we're going to look to see that this is a -1, so h is going to be 1, so we get 1 for the x value, and then +5, so we get +5 for the k value. All right, so we know we have the vertex of 1, 5, so we're going to go over 1 and up 5. And there's our vertex right there of 1, 5. All right, next what happens? Next we're going to take a look and see that we can find the axis of symmetry. So the axis of symmetry is that x is going to be equal to 1. All right, so we're going to come up here and we're going to sketch this. All right, there's our axis of symmetry at x is equal to 1. Okay, so again, we have a parabola that's open upward. We found the vertex of 1, 5, and so we've graphed that and we've looked at the axis of symmetry. All right, so next what we want to do is we want to find the x-intercepts if they exist. So again, we have this point 1, 5 here as our vertex, and we have a parabola that's opening upward. Okay, so we want to find the x-intercepts. So what happens at the x-intercepts? Well, y is equal to 0. So we're going to have 0 is going to be equal to 3 times x minus 1 quantity squared plus 5. Now, the first instinct of most people here is to say, well, gosh, I've got to solve this. I've got an x minus 1 squared. And most people would try to square that right away. But I'm going to show you a different method here of doing this that you may have seen before. And what is, we're going to work with the square term here. And so what we're going to do is we're going to first of all subtract 5 from both sides of the equation. So I'm going to subtract 5. So I've got minus 5 is equal to 3 times x minus 1 quantity squared. Okay, so far so good. Next I'm going to divide by 3. So we're going to divide both sides of this equation by 3. And so we get negative 5/3 is equal to x minus 1 quantity squared. Well, some of you are probably seeing already what the problem is here. The problem is that we can't square something and get a negative. But if we want to complete this out to verify that for ourselves, if we take the square root of both sides, the square root of negative 5 over 3 is equal to the square root of x minus 1 squared. Okay. Now we remember that what happens is we take the square root of something that's squared, we need to put our plus and minus out in front here. All right, so we're going to say, hey, that's kind of similar to what's happening in the quadratic formula if we had solved this by quadratic formula. Okay, but what happens? We get plus or minus the square root of negative 5/3 is equal to x minus 1. Well, if we want to continue on with that, we can add 1 to both sides. So we're going to have 1 plus or minus the square root of negative 5/3 is equal to x. But we're going to say, wait a minute, could we have stopped way back up here? Yes, we can. But we've completed this out. For those of you who might want to try this problem of expanding out the term x minus 1 and squaring that, and then expanding this whole expression out to put it back in the general form. If you were to do that and use the quadratic formula, you get a similar answer. Now, I know I have something here that's happening where I have a 3 in the denominator, so we would probably want to rationalize that, but I'm not going to do that here because I'm looking at this and saying right away, I know this is not a real number. Okay, so this is not a real number. So therefore, there are what? That happens, so we have no real x-intercepts. Okay, so we're not going to apply anything. And remember, that makes sense because what happens? Our graph is opening upward as we've shown here. And since it's opening upward, I'm just going to put a dashed line in here, and we'll figure out some of the other points here in just a second. Since it's opening upward, it's not going to cross the x-axis. So therefore, there's no real x-intercepts. Now, this is not going to happen every time, but you could apply the same method of solving the square in finding your x-intercepts. In many cases, you will get a real number value in there that you have to plot. But as I had said earlier, that sometimes you get these non-real solutions for your x-intercepts, and so therefore you want to be aware of that. Okay, so the only thing we can do is to move along and take a look at our y-intercepts and possibly use our axis of symmetry here. All right, so let's go ahead and do that. We've already solved that. Okay, so again, we have the 1, 5 is our vertex, and so we want to solve for our y-intercept. So our y-intercept is where what? X is going to be equal to 0. And so on the x be equal to 0, we end up with f of 0 is equal to 3 times 0 minus 1 quantity squared plus 5. Okay, so when we let x equal 0, we're going to see that this comes out to be, the y-intercept comes out to be 8. All right, so we can plot that point up here of 8, 0. Put that on our graph. Let's put it nice and big. There's our vertex of 1, 5, and here we have, excuse me, that should be 0, 8, not 8, 0. That's our y-intercept, so the 0 is our x-coordinate, and so we have 0, 8. Now, the question becomes, again, we need to find another point. So we're going to use the axis of symmetry again to do this. And so we're going to come up here and say, here's our axis of symmetry, and if you recall, in the previous program what I did, I said we're going to take a look over here and see that our y-intercept is what? 1 unit to the left of our axis of symmetry. So if we go 1 unit to the right of our axis of symmetry, we should have another point there. And in fact, that point will be the point 2, 8. And we can verify that by plugging 2 into our equation here. If you did f of 2, you'll get 3 times 2 minus 1 there, and 2 minus 1 squared in parentheses plus 5, and this is basically going to give you what? 3 plus 5, which is going to give you 8. And so we see we have that point. So now we can clean this up and we can graph our parabola, and it's going to be kind of narrow here as it goes up, and so we can connect and again put arrows, and we've graphed our quadratic function in standard form. Okay, so that completes our graphing of quadratic functions in our in standard form and how they look, and we can see that the techniques were very similar to what we saw previously in working with the quadratic functions in general form. So we have this several-step process that leads us to getting the graph. And again, you can plug this into your calculator to do on your calculator. However, it's worth looking at finding the exact values, because sometimes, as I've mentioned previously, you don't have the exact values coming through on your calculator very easily. This ends our presentation on looking at the standard form of a quadratic function. And here we know that we just defined the standard form of a quadratic function. We examined the properties of the standard form of a quadratic function, and finally we graphed a quadratic function in standard form. In our next program, we're going to take a look at a couple applications of the quadratic functions and see how we can actually use this information to achieve solutions to particular problems that we might be interested in solving.